Hello there, and welcome back to Chemistry for Engineers with Jen Termel. We are beginning chapter 8, and we're going to be looking at molecules and materials chemistry, some very interesting stuff, metallics, crystals, and this will be a longer chapter. It'll probably be 3 videos. So here is part 1. All right, here we are on slide 2, and I've numbered them ahead of time this time. And we're going to start by talking about carbon. Carbon is, there are a variety of different forms, but we're going to be looking at 3 main forms of elemental carbon here. The first one is graphite, and then diamond, and then something called fullerenes, which are pretty important. So carbon has been really important material for a lot of different applications. So just a few common ones here is that diamond is used in things like drill bits, jewelry, diamond saws, that kind of thing. Graphite, is used in pencils, but it's also used as a lubricant and as a composite material. And then the bottom one here says that applications of fullerenes and nanotubes are still being explored. But the carbon-based nanotubes and fullerenes is so interesting. That's where you get things like carbon fiber. And while they say they're still being explored, I am a violinist and a violist in sort of my other life, and I own a carbon fiber violin bow. And so I just think that these are so fascinating because it's a way that engineers are basically changing um, the planet for the better. Violin bows, cello bows, viola bows, bass bows. The very expensive ones are made out of Brazil wood or Pernambuco, which is it's a limited resource. It's rainforest wood. And so the more bows and things like that can be made out of carbon fiber, basically saves us from cutting down trees in the rainforest. So that's the kind of thing that engineers are working on right now, which personally I think is very interesting. All right, slide 3. So now let's talk about that carbon fiber, also sometimes known as graphite fiber. It's a polymer of carbon. And again, remember, I think we've talked about this before. Polymer means many molecules. So it's kind of this long chain of carbon atoms added together and strung together to make something that is very thin with very strong crystalline filaments of carbon, and that's used to basically strengthen the material. Carbon can be 5 times stronger than steel. Okay. It has it's high in stiffness, chemical resistance, and tensile strength. Those are the things you want in building materials. Um, but then this is what's really interesting is it has a really low weight to strength ratio. So steel is really heavy. So when something has a low weight to strength ratio, that means basically that the strength of your material is high, and then the weight or the mass of your material is low. And that basically means that you can make things that are very strong but don't weigh nearly as much as a metal or something, which again is worse for the environment to use. Okay. Some other really important things about carbon fiber is that they are temperature tolerant to excessive heat. Back to that violin bow that I own, you have to be very careful with wooden instruments because they really do not like the extreme changes in temperature, but carbon fiber doesn't have that same problem. So it doesn't affect the bow so much. A very good colleague and friend of mine is a professional violist, and she owns a carbon fiber viola, which is absolutely fascinating. So again, these things where you would think engineering and you wouldn't necessarily think that it's making its way into the musical world. It also has low thermal expansion, which kind of ties in with that temperature tolerance. All right, so this is a picture of our carbon nanotubes as a type of fullerene. And you can see this really amazing way that it's shaped like this. It makes this fascinating tube. And the importance here is that, so let's take a look at what a couple things are. Tensile strength is the maximum amount of stress that a material can withstand while being stretched or pulled without breaking. Okay. Now, carbon nanotube tensile strength is significantly higher than the tensile strength steel, which is one of the ways that it makes it just so strong and able to be manipulated. These nanotubes can be grown. So you can see this nanotube makes this cylindrical shape. And what you could do is you could put metals inside these tubes, okay? And that'll make a wire that is only about 1 molecule wide. So a single molecule of metal inside a carbon filament here makes a wire with a carbon filament around it. And it's very, very small, which it has amazing applications within computers and a bunch of other things as we shrink down our technology. All right, so let's take a look at carbon just as a compound, okay? So this is what's known as a phase diagram. And a phase diagram shows which state or phase of a compound or element will be most stable at a given temperature and pressure. So we're in kelvins, okay? And this is a straight scale, so 2,000, 4,000, so right about 4,000 kelvins is where graphite can become vapor, or just a little higher than that becomes liquid. And under great amounts of pressure, so this pressure is logarithmic. So this is 10 and then 100 and 1,000. So the pressure is increasing faster than it looks like it's increasing because it's increasing by a factor of 10 every single one. And the really interesting thing here is that carbon has 2 triple points. And this is what's called a triple point, and this is a triple point. And a triple point is a place, most elements do not have more than 1 triple point because they don't have these 2 main forms of solid. So this is a solid up here in the diamond region, and our graphite is a solid. And so we have 2 triple points. And a triple point is a place where all 3 forms exist at once. Okay, so at this point, for temperature and pressure, you can get solid graphite, liquid carbon, or gaseous carbon. And then at this triple point, which is about the same temperature but much higher pressure, you'll get solid diamond, solid graphite, and liquid all at this temperature and pressure. All right, we are on slide 6. Okay, now let's take a look at what we would call condensed phases. Okay, condensed phases are solids and liquids, basically anything that's not a gas. Okay, but let's take a look specifically at the condensed phase for solids. Okay, in these, atoms and molecules arrange themselves into 2 different types in a condensed phase solid. One is a crystalline solid, and a crystalline solid is going to have atoms or molecules that assume a regular repeating geometric arrangement. Okay, and it's regular, it's repeating, it forms a crystal structure where each part of the crystal basically looks the same as all the other parts of the crystal. An amorphous solid is much different. The atoms or molecules in an amorphous solid forms a random crystal, a random solid arrangement, which basically means that everything is just shoved in there as it is. So when you have an amorphous solid, one part of the solid and another part of the solid might look slightly different in their molecular or atomic arrangements. So in crystalline solids, because we have a regular repeating crystal structure, we can have them basically be a tighter set or a more open structure. Okay. And what we use to describe that is something called packing efficiency. This is the percent or percentage of the occupied space in an arrangement. So the higher the packing efficiency, the higher the density. Okay, so in these marbles right here, Okay, we have large gaps right here for our A, and these large gaps will get us in these marbles a 78.5% packing efficiency. Okay, and that means that 78.5% of the space is marbles. But when we offset, so this is stacked one on top of each other in what we call aligned rows. But over here, we have smaller gaps. And that's because we don't have aligned rows, but we have offset rows. And so when we offset our rows, now we have a 90.7% packing efficiency, which means 90.7% of the space is taken up by the same marbles. And so again, that's going to help you determine things like density, and mass, and your flexibility, and all different kinds of things can be linked to packing efficiency. Now let's take a look specifically at some more crystalline structures here, some crystalline solids. Got to make sure that I'm on the right one. We're going to be looking at how we can maximize our packing efficiency. Okay, so for maximizing packing efficiency right here, we can see a couple different methods here. So first one, here we have everything is offset just a little bit, okay? So you can see that layer 2 here is offset like so, okay? And then layer 3 is offset like so. Now, layer 4 right here, okay, this one comes straight down like this and stacks directly over the first one here. Let me actually change that color. Okay, so here you can see that in this structure, our third, so if this is our ground layer or our base layer, and then layer 1, 2, and 3 above that, this third layer here in our hexagonal close packing is straight above our base layer down here. Okay. All right. Now let's take a look at our cubic close packing. I think I got these mixed up. Hang on. Okay. So to look at my slide. Okay. So in this one, I was numbering them incorrectly. So let's go ahead and start again. Okay. So here, let's layer these correctly because this wasn't real clear. Okay. So here we have, let's take this in pieces. Okay. So in both of these, we have our second layer right here directly above the hollows in the first layer. And you can see that that is the case in both of these. Okay. So layer 2 is above the spaces or the hollows in both of them. Okay. Now, in our cubic closest packing structure, which is right here, you can see that this is still directly above some hollows here. Okay, because we're overlapping. Okay. And so we keep staggering. So we're always we're always offset a little bit in our cubic close packing. So each one is set off a little bit. Now in the hexagonal close packing structure, excuse me, you can see that this one is over the hollows here, but we're straight over just 2 layers down. So in our hexagonal close packing, we link layer 1 and layer 3. But in our closed packing, which is here, we link layer 1 and layer 4. All right, here we are up to 9. So let's take a look at the different packing for unit cells. In these unit cells, we can see a few different things here, okay? So in a simple cubic unit cell, you have basically just a cube on the center. And you can draw a cube through what you have here. And, okay. And you can see how this works out. And they're touching on where they are here. So a simple unit cell is 1/8 of each of 8 corner atoms, and it has 1 atom per unit cell. Now, in a body-centered cubic cell right here, or BCC, we have the same stuff. We have 1 atom for each one of the corners, and that's not going to change. We have a, a molecule right here in the center of the unit cell. So this is 1 atom plus 1 in the center for 2 atoms per cell. Okay. Now over here we have our face-centered cubic, and our unit cell for this is a little bit expanded. And what this is doing is these are right here are on each face. So you have 6 atoms on your faces, and half of each one is in our unit cell. So we have 1 atom plus 3 on our faces for 4 atoms per unit cell. So this is just another way to look at that, how to calculate that. Calculating the atoms per unit cell. And the thing to remember here, we have in our face-centered cubic, we have 4 atoms per cell. And in our body-centered cubic, we have 2 atoms per cell. This is just review from the last slide. And in our simple cubic, we have 1 atom per cell. And the thing to remember that the total volume occupied by the atoms, or the number, is the number of atoms per unit cell. So again, this is volume of our atoms in the cell is equal to the number of atoms in the unit cell times 4/3 pi r cubed. All right, let's take a look at slide 11. Okay, so now, so just to remember, okay, so we have our volumes from the last chapter. Okay, so just as a little reminder there to go back again, the volume of our atoms is equal to the number of atoms times 4/3 pi r cubed. Okay, where r is atomic radius. Okay, and now this is the volume of our unit cell. So this is the volume of our unit cell is what this V is. And it's A cubed, where A is the edge length of the cell. So what do we mean by that? Here's our unit cell. It's always going to be, however it is. In this case, we're only doing cubic cells. And this is A and A and A. And here we have the the side lengths of each one already calculated out for you. So the A value for a face-centered cubic is 2√2r, okay, where r is still your the radius of the atom. Okay. And then you have the edge length of a body-centered cubic is 4 over the root 3 of R. I don't know what these are showing here. Okay. And then we have the edge length of a simple cubic at 2R. And you can calculate your packing efficiency by doing volume of atoms in a unit cell divided by the total volume of your unit cell times 100. All right, so let's do some problems with packing efficiency. Okay, so what we're going to do here is we're going to calculate our values here for packing efficiency for our 3 main cubic structures. So when you're dealing with a simple cubic unit structure, remember that the A for a simple cubic is 2R, okay? And that the volume of our cell then is going to be 2R cubed. Okay. So the volume of our atoms divided by the volume of our cell times 100%. Okay. So the volume of our atoms is going to be 1 atom times 4/3 pi r cubed divided by 2r cubed for the volume of our cell. Okay, so this comes, I'm going to show you all the fun algebra for this. So we have 4/3 pi r cubed over 8r cubed. Okay, so now let's look at how this gets canceled. So we can cancel our r cubed, and 4 becomes 1 and 8 becomes 2. So now we have pi over 3 times 2, because this 3 goes into the denominator here. So we have pi over 6. And then we take our pi over 6 and we times that by 100%. And on the calculator, that will give us 52.36% packing efficiency for our simple cubic structure. All right, now let's look at our body-centered cubic structure. And in a body-centered cubic structure, remember that our A value, our edge length, is 4 over the root 3R. Okay, so again, it's the volume of the atoms over the volume of the cell. And I'm getting these formulas from previous slides times 100%. And now body-centered cubic has 2 atoms per unit cell times 4/3 pi r cubed over the volume of our cell. So that's going to be 4 over root 3r cubed. All right, so let's work through our math here. So now we have 8/3 pi r cubed divided by 64 over, oh, I forgot, look, this is supposed to be a square root there. There we go. 64 over 3 root 3 r cubed. Okay. Now let's go ahead and we'll cancel things out again. Here we can cancel out. Let's undo that. Needed to change colors to cancel. Cancel out our r cubed. The 8 becomes a 1 and the 64 becomes an 8. And we can cancel out these 3's right here. And now we are left mathematically with pi over 8 over the square root of 3, okay, which becomes square root 3 pi over 8. And then times 100%. And this gives us a packing efficiency for a body-centered cubic of 68.02%. All right, and now last but not least, let's work through our face-centered cubic. And the volume of our atoms over the volume of our cell times 100%. Okay. Now, in a face-centered cubic, we have 4 atoms times 4/3 pi r cubed divided by the volume of our cell. And just to remember here that our edge length A is equal to 2 times the square root of 2r. And so this becomes 2 root 2r cubed. Okay, and when I calculate this through, then on the top we get 16 over 3 pi r cubed. And on the bottom, we get, so when you go 2 root 2 cube, what this becomes is you have, just to show that math, is 2 times 2 times 2 times root 2, root 2, root 2. So that becomes 2 times 2 times 2 times 2 root 2. If you're just wondering where I'm doing this, okay, so that becomes 16 root 2 r cubed. And if you're wondering why I'm doing all this like this instead of on the calculator until the very end, when I was working through this math at home, because as you can see, I actually work through all of my math myself. I don't use a key. I'll verify my answers, but I don't use a key because I like math. And when I'm working through this, if you work through your basically your math, that pure math before you pull out your calculator, you will get a slightly more accurate value. If you start rounding as you go, you might get an answer that's less accurate. And so you really don't want to pull out your calculator until the last possible moment. Okay. Now, in this one, we go here and we're going to go ahead and cancel out a couple things. And first, again, we can cancel out our r cubed and we can cancel out our 16. Right now, as you've seen before, this 3 is in the denominator, so that'll come down. And this will become pi over 3 square root 2. And we multiply that by 100%. Which will give us 74.05% for the packing efficiency of a face-centered cubic structure. Excuse me, I have hiccups. Okay. Couple more slides with a lot of math. Hopefully you like math too. And you probably do if you're going to be an engineer because engineers do a lot of math. Okay, let's practice a great, big, huge, fun problem. So in this problem, we have the fact that europium forms a body-centered cubic unit cell, and it has a density of 4.68 grams per centimeter cubed. And we want to know 2 things. We want to know the volume, and we want to know the edge length of our unit cell. Okay, so let's go ahead and take a few moments here. So take good notes. Remember that once you have taken good notes, you may take pictures in class of my notes to add to your notes. But I do want people taking those notes first. Okay, so first of all, our step 1 is to determine how many units or atoms per cell. And because this is a body-centered cubic unit cell, we have 2 atoms per cell. Now, our step 2 is to find the molar mass of our element. Okay, and if you look on the periodic table, you will see that europium has a molar mass of 151.96 grams per mole. Now, our step 3 is to use our density to determine how many atoms are in a single cubic centimeter. And so we do that by saying, okay, we have 4.68 grams per centimeter cubed. And then we're going to use our molar mass, and that's 151.96 grams per mole. And then we're going to use Avogadro's number that tells us that we have 6.022 times 10 to the 23rd atoms per mole. Now let's see how this cancels. Okay. So our grams cancel here and our moles cancel here, and we are left with atoms per cubic centimeter. And when we calculate this through on the calculator, we get 1.85 times 10 to the 22. And this is atoms per centimeter cubed. Okay. Now, step 4 for this problem is to set up a proportion to find the volume of the atoms in a unit cell. And we're going to do that by doing 1.85 times 10 to the 22, and that's atoms per 1 centimeter cubed, equals, that's a proportion. So remember, a proportion is two ratios linked together, equals 2 atoms. And this was the volume down, we have the bottom. And so we're going to have the volume of our cell down here. Now to solve for that, we cross multiply, and we have that the volume of our cell then is equal to 2 atoms times 1 centimeter cubed divided by 1.85 times 10 to the 22 atoms. And when we calculate that out, we will get 1.08. Again, be pausing this as you're writing it and calculating it through to see that you get the same values that I get. 1.08 times 10 to the negative 22 cubic centimeters. And that is our first answer up there, asking for the volume of our unit cell. Okay. Now our step 5 is to go a step further and find our edge length. So remember that the volume of our cell is equal to A cubed. So we can find our edge length A by taking the cubed root of our volume, 1.08 times 10 to the negative 22 centimeters cubed. And that will give us an edge length of 4.76 times 10 to the negative 8 centimeters. And there we have our second answer for edge length. Now, it's not asked in here, but we could go a step farther and find radius as well. So to find the radius of our atom, we can actually use this piece of information to find that. And we would do that by saying the A value for a body-centered cubic, remember, is equal to 4/3 R. Wait, is it? Hang on. I'm going back and looking at it. No, it's 4 over the square root 3 of R. Okay. I actually need a calculator because I haven't done this. I have my calculator now. So we have 4√3 R, and then we will solve by for R, okay, there we go. We will solve for R by doing the square root of 3 times A, which I have right there, over 4. And so R equals the square root of 3 times 4.76 times 10 to the negative 8th divided by 4. Okay, and I can calculate that by doing root 3 times 4.76 times 10 to the negative 8th. All right, divided by 4. And that will get me a value of 2.06 times 10 to the negative 8th centimeters. I'm just making a note of it for myself. There we go. Okay. All right, another fun challenge problem. And here we are talking about gold. And gold has a face-centered cubic unit cell and a radius, oh, if you can't see that, it's printed on your sheet, of 0.144 nanometers. And we want to know what the density of our unit cell is. All right, so let's go ahead and work through our steps again. All right, so our step 1 in this case is going to be, again, how many atoms per unit cell? And for a face-centered cubic, that is 4 atoms per cell. Going to do here in step 2 is I'm going to convert my radius to meters. And so I have 0.144 nanometers times 1 meter on the top and 1 times 10 to the 9th nanometers on the bottom. You've got your charts in chapter 1 if you can't remember that. And that gives me 1.44 times 10 to the negative 10th meters. My step 3 is to find my edge length. So my A of my face-centered cubic is equal to 2 square root 2r. And so that is going to be equal to 2 times the square root of 2 times 1.44 times 10 to the negative 10th. Which is going to give me 4.0. Now, you'll notice here what I'm doing is I'm going to give myself extra significant figures until I get to the end. That's because there's a lot of calculations and I don't want to lose any of my accuracy. So I get 4.072935 times 10 to the negative 10th meters. My step 4 is to find the volume of my unit cell. So here I have the volume of my cell is going to be equal to A cubed. So that's going to be equal to 4.072935 times 10 to the negative 10th cubed, and which is going to give me 6.7565 times 10 to the negative 29th meters cubed. Now, actually, you notice that I probably should have gone to centimeters in step 2. If I had calculated to centimeters in step 2, I wouldn't need to do step 5, but I didn't because I'm in meters cubed. Now my step 5 is to convert my meters cubed to centimeters cubed. Now, to do a cubic conversion, it's a little bit different because it's not just 100 centimeters per meter anymore. So we would start out with 6.7565 times 10 to the negative 29th cubic meters. And in order to do a cubic conversion, you have to put 1 meter and 100 centimeters in a cube. And then you have to cube this and then multiply it. And that will give you 6.7565 times 10 to the negative 23 cubic centimeters. And that's because the density of a solid is always going to be in grams per cubic centimeter. And that's why we had to go to centimeters cubed. We couldn't leave it in meters cubed. Okay, so now we have step 6. And that is to find the mass of a unit cell. So remember that gold from the periodic table has a mass of 196.97 grams per mole. And so now we'll find that mass by doing 4 atoms of gold times, now this is where we use Avogadro's number in this problem, 6.022 times 10 to the 23rd atoms per mole. And then our molar mass, which is 196.97 grams per mole. And you can see how everything cancels. And I will get a mass value here, value of 1.3083 times 10 to the negative 21 grams. And finally, my step 7. All right, let's identify a couple things here. First of all, this is my volume. And this is my mass. Because here at the end, I am going to be calculating density. And density, remember, is mass over volume. And so now I can put in my mass of 1.3083 times 10 to the negative 21 grams over my volume of 6.7565 times 10 to the negative 23rd cubic centimeters. Verify on your calculator that you're doing this correctly. And now you take a look and I see that I can only have 3 significant figures. And when I do this, this division, I get 19.4 grams per cubic centimeter. And that is our final answer for the density. All right, that is the end of part 1. I will see you in part 2.